When we fire electrons through a double slit at extremely low intensities, each electron registers on the detector as a single localized dot. But as those individual strikes accumulate, tens of thousands of dots organize themselves into a distinct interference pattern. The electrons arrive as discrete particles, yet collectively behave as a wave. A set of classical coordinates, recording exact positions and precise momenta, cannot account for this outcome. A mathematical point has no physical extent, meaning it cannot pass through two slits at once, nor can it interfere with itself to produce the alternating fringes we observe on the screen. To resolve this, we require a richer mathematical object. We introduce the wave function, denoted by the Greek letter psi. It is a function of both position and time, capable of spreading and carrying the phase information necessary to produce interference. We are no longer calculating trajectories. To predict the behavior of a quantum system, we must track and evolve its wave function. Defining what that wave function actually represents fell to Max Born in 1926. He argued that the wave function is not a physical vibration in space, like a sound wave or a ripple in water. Instead, it is a complex probability amplitude. Because the wave function contains imaginary numbers, we can never observe it directly. Only its squared modulus touches the physical world. This yields the probability density, providing the exact likelihood of finding a particle at a specific coordinate in time. This establishes a highly unusual arrangement between the mathematics and reality. The physical system is completely described by unobservable complex numbers, which we use to perfectly predict observable statistical outcomes. To understand how this state evolves, we rely on the time-dependent Schrödinger equation, the central equation of motion in quantum mechanics. On the right side of this equation is the Hamiltonian, the operator that represents the system's total energy. It breaks down into two distinct parts. The first is the kinetic energy, which is driven by the second spatial derivative. The sharper the wave function curves, the higher the kinetic energy of the particle. To this, we add the potential energy term, representing the physical constraints or forces acting upon the system. On the left side of the equation, we find the first-order time derivative. This determines the exact rate at which the wave function updates from one instant to the next. And accompanying that time derivative is the reduced Planck constant, multiplied by the imaginary unit I. Notice the structural asymmetry here. The equation is second order in space, but only first order in time. Without that imaginary unit, a differential equation with this structure would yield simple exponential decay, flattening the wave out to nothing. The inclusion of I ensures the solutions rotate and oscillate. The wave function must take complex values because the physics of matter demands an oscillating wave, and this equation is the only way to generate one. For many physical systems, the potential energy landscape does not change. The walls of a container or the electrostatic pull of a nucleus remain static over time. Under these static conditions, we can solve the equation using a standard mathematical technique called separation of variables. We propose a solution that splits the wave function into the product of two completely independent functions, one mapping space and one mapping time. By substituting this product back into the Schrödinger equation and dividing both sides by the total wave function, we force all the temporal variables to the left and all the spatial variables to the right. Because the left side depends only on time and the right side depends only on space, the only way they can remain equal is if both sides equal the exact same constant. In this case, that constant is the total energy of the system, E. This isolates the spatial component into its own relation, the time-independent Schrödinger equation. Structurally, this is an eigenvalue problem. The Hamiltonian acts on the spatial wave function and returns that exact same function, scaled by the allowed energy level. The specific functions that satisfy this boundary condition are known as stationary states. They are the fundamental, allowed modes of a quantum system. When we reattach the time component to our spatial solution, the total state becomes the spatial wave function multiplied by e to the negative iet over h bar. By Euler's formula, that exponential term acts as a rotating phase in the complex plane. Looking closely at this graph, the top panel tracks the real part of the wave function as time advances. It oscillates wildly between positive and negative values. Simultaneously, the middle panel plots the imaginary part, oscillating exactly 90 degrees out of phase. Together, they operate as a complex clock, constantly dynamic, mapping a continuous rotation through mathematical space. But remember Max Born's postulate: the wave function itself is completely unobservable. To find the physical probability, we must square the modulus, which means multiplying the wave function by its complex conjugate. When we do this, the opposing time-dependent phase factors perfectly cancel each other out, leaving a value of 1. The probability density of the total state is therefore identical to the probability density of the spatial state alone. The time dependence vanishes entirely. Compare this to the dynamic components above it. In the bottom panel, you see the probability density. While the real and imaginary phases rotate furiously, the density curve remains perfectly static. The physical reality, the likelihood of finding the particle at any given coordinate, is completely frozen. This is why we call them stationary states. This static probability density still has a physical shape, and its width represents the spread of possible positions for the particle. Because position and momentum are linked by the wave function's curvature, any state with a finite width in space must also have a finite width in its possible momentum values. This relationship defines a hard floor for uncertainty. For any state, the product of these two spreads must be at least h bar over 2. This plot shows how various states compare to that limit, reaching the absolute minimum allowed. By factoring out time, the Schrödinger equation identifies the precise spatial frequencies that can exist within a given potential, transforming a complex rotating wave into the stable, discrete energy levels we observe in nature.